Okay, we might get started, everyone. So hello, everyone, and welcome to another presentation as part of our series on meta science in skill acquisition. Today, joining me is Cristian, who is going to be talking about why ethical research should be credible and whether us as researchers are actually following some of the recommendations that are detailed in the Declaration of Helsinki. I've been really interested in some of Cristian's recent work around exploratory research and why we should be looking to do more credible research in sport and exercise science, and how some of the research that we're doing may not necessarily be replicable, and what the implications are for practice. So the structure for today is around a 40 to 45-minute talk followed by some questions. If you have a question and you don't want to ask it specifically, just chuck it in the chat and I'm more than happy to ask it at the end. But without further ado, welcome, Cristian.
Okay, perfect. Thank you so much for having me. Can I share my screen already?
Yeah, you should be able to share your screen. I've added you as co-host.
Can you see it?
Yeah, it's just loading in now. Yep, looks good.
Yeah, it's good to go.
Yeah, good to go.
Okay, perfect. Well, so yeah, again, thank you so much for having me. My name is Cristian, and I'm a postdoctoral researcher at Eindhoven University of Technology. My background is in exercise science as well, and I did my PhD on the replicability and reproducibility of sports and exercise science research. And today I'm gonna be talking about whether the research that we are doing in the field is credible and ethical. And to make the point, we are gonna be talking about a little bit about the Declaration of Helsinki. So just briefly, those are the discussion points that I'm gonna cover. So we are gonna get started with the Declaration of Helsinki, what it is. Then we are gonna move to informative research versus research waste. So we'll be talking about the differences and what makes research waste. Then we are going to be talking about different types of research waste, basically where it goes wrong in the research cycle, and then potential reasons, and then finally potential solutions. So just to get started, so basically the Declaration of Helsinki was developed in 1964 by the World Medical Association, and it serves as the international benchmark for ethical conduct in human research, providing principles that guide regulatory bodies, research institutions, and individual researchers. And now I have just two questions. You don't need to answer, but it's always interesting to know how many researchers do know the content of the Declaration of Helsinki, and if so, how many of you have declared to the Declaration of Helsinki in your research? Because, for instance, for me, in my early research, I remember some of the studies where we declared to the Declaration of Helsinki. But now, in hindsight, I do know that we didn't adhere to the Declaration of Helsinki. So even if we stated in the published paper that we were adhering to it, now I'm aware that we didn't do it. And then it's that as a researcher or a master student, that you are collecting data, you are collecting data from humans, or participants, you don't really know the content of the Declaration of Helsinki. So you may have a very vague idea of what it is, but personally, I never studied, I never read it, and I don't think there was any emphasis or any mention in any research methods course about the content of the Declaration of Helsinki. So just briefly, the Declaration of Helsinki is updated every couple of years. Now I'm going to show you two points from the Declaration of Helsinki in 2023. So the point 12 say that medical research involving human subject must be conducted only by individuals with the appropriate ethics and scientific education, training, and qualifications. I will get back to this point later on the presentation, but it's worth keeping in mind. Then another point is that medical research involving human subjects must conform to generally accepted scientific principles, be based on thorough knowledge of the scientific literature, other relevant sources of information, and adequate laboratory and as appropriate animal experimentation. Again, we will get back to this point later on the presentation. Now I'm going to show you two additional points from the latest version of the Declaration of Helsinki, which was released in 2024, but it was published in 2025 at JAMA. So for first time, it makes a direct reference to research waste. So it says that medical research involving human participants must have a scientifically sound and rigorous design and execution that are likely to produce reliable, valid, and valuable knowledge and avoid research waste. And then finally, and sorry for the reading, researchers, authors, sponsors, editors, basically stakeholders all have ethical obligations with regard to the publication and dissemination of results of research. Researchers have a duty to make publicly available the results of their research on human participants. Again, we will get back to these 2 points later on the presentation, but please keep them in mind. So, as opposed to research waste, what is informative research? So, informative research is the process of gathering and analyzing data to produce reliable knowledge. It's carried out through ethical and rigorous methods and communicated transparently without bias, enabling peers to verify and build upon the findings. So why do we do research? So let me take a very medical point of view. So basically we do research to test the efficacy or effectiveness of interventions. And a very good example is intervention A more effective than intervention B in reducing time to return to play in football players after injury? So that will be an example of researchers being interested in the efficacy of an intervention. So what is research waste? So exactly the opposite. So it will be research that fails to produce reliable or relevant results that cannot be used to inform decision making. And now let me get started with the topic of research waste with this paper that it was published in 1994 at the British Medical Journal by Altman. And he made a very clear point. He made the point that it would be a scandal that surgeons used substandard medical techniques to treat patients. And even that, he said that the medical literature was full of studies that used substandard techniques or methods that did not contributed to knowledge or to the improvement of treatments. So waste can occur at 4 stages. We will cover every single stage here, but so you know that the waste can occur at the question or the hypothesis that researchers are testing. It can occur at the design and analysis stage, at the reporting of results, and the dissemination of the studies or publication. So let's get started with the research question. Why the research question can contribute to research waste? So because it's irrelevant, or the question it's not very interesting, or it's redundant. And let me show you an example from medical research. So that there was a meta-analysis published in 1992 on the effect of therapeutic trials on myocardial infarction. And those are the key points that I would like you to be aware of. So 33 trials evaluating this therapy were performed between 1959 and 1988. A statistically significant reduction in mortality in odds ratio was achieved in 1973 after only 8 trials involving 2,432 patients. The results of the 25 subsequent trials, which required in addition to more patients, so 542 additional patients were recruited through 1988, had little or no effect on the odds ratio establishing efficacy, but simply narrowed the 95% confidence interval. 2 very large trials in 1986 and 1988 did not modify the already established evidence of efficacy. So now I'm going to show you a forest plot here, and we can see that around the 8th trial, which will be here, the treatment showed a statistically significant reduction of the mortality. Okay, but even then researchers continued to publish or to perform randomized controlled trials until 1990 for a total of 46,000 patients. Okay, so the point that I want to make is that it's important to narrow the confidence interval, because you can be more certain about where the effect is, but it doesn't change in any meaningful way the conclusion of the meta-analysis published in 1973, because it already reached statistical significance, and then basically it hasn't changed in any meaningful way. So now let me use an example in sports and exercise science. That was a meta-analysis on the effect of self-talk intervention on sports and motor performance, which was conducted by Corcoran and Steele in 2024. So since this meta-analysis published in 2011, the number of studies conducted examining the effects of self-talk interventions on sport performance has roughly doubled. 35 new studies published from November 2011 up to November 2023. And the overall effort in the meta-analysis published in 2011 was an effort size of 0.48 with a confidence interval ranging from 0.38 to 0.58. And after adding newer studies, the overall effort was 0.47 and the confidence interval ranged from 0.39 to 0.56. So this showed that even after adding 35 new studies, the confidence interval and the effort size barely change. Okay, so here one can question whether these new studies contributed to the literature in any meaningful way. So the point that I want to make is that new research should be set in the context of an evidence gap and should involve a stakeholder when possible. Stakeholders here, I mean authors, researchers, participants, patients, research institutions, all those all those should come together and made decisions about what research lines should be prioritized in order to inform future research studies. So now we are going to move to the next stage where research waste can occur. This is the study design phase. And the consequence is that researchers might conduct studies that do not answer the research question that they wanted to answer. So just two examples. So for my PhD, we used a sample of 350 studies published across 10 journals in sports and exercise science. And from each one of these 350 studies, we extracted the statistical test that it was central to the hypothesis being tested. And out of the 350, 23 studies tested the hypothesis of equivalence using a classic null hypothesis test. Just for those that are not familiar with equivalence testing, an hypothesis of equivalence is when researchers want to test whether two interventions don't differ by a certain margin. So what you want to prove is that these two interventions are equivalent as opposed to different. And for that, you should be using an equivalence test. And then another example is testing for treatment effects by separate analysis of change from baseline in each group, which is a misleading approach. So here, this figure may illustrate the point that I want to make. So when you want to compare two interventions, for instance, and there is a pre-post measurement for each condition, you are interested in the interaction, which is the difference in the difference. So you are interested in the difference between pre-post versus the difference in the pre-post between the two conditions or interventions. But usually what happens, or not usually, but it happens more often than it should, is that a researcher use the difference or the statistical significant difference in the experiment condition, and when this difference reaches statistical significance, but this difference, it doesn't reach the statistical significance, they claim that there is a difference in the two treatments. But this is misleading because if you then perform the interaction test, you will obtain or you may obtain a result that denotes or that denotes that the two treatments are not statistically different. Another reason why a study design is important is because researchers need to plan the sample size or the number of participants that they aim to recruit. And in my experience, this is where very often goes wrong, because in my experience, and this is a study that we did as part of my PhD, many a priori power analyses are invalid. So what we found is that the mean samples, for this study, we used the same sample of studies that I showed you before. So this relates to the 350 studies that tested an hypothesis and were published across 10 different journals. So what we found is that the mean sample size of these 350 studies was about 30 participants. Then we found that 40% of the hypothesis testing studies reported conducting an a priori power analysis. We didn't find a significant difference in sample size between a study that reported an a priori power analysis and those that did not. So you will expect, or yeah, I will say you will expect that because the sample sizes are usually very small in sports science, if you conduct an a priori power analysis, you will expect that those studies that conduct an a priori power analysis should report a larger sample size. But we didn't see that. And then also assuming that both types of studies test the same proportion of hypotheses that are true, you will expect that if you conduct a study with an a priori power analysis, those studies should report a higher proportion of hypotheses supported. But we didn't find that. And then we came to the conclusion that the reason is that in many occasions, studies that report an a priori power analysis, those a priori power analyses are invalid. And there are several reasons. So several reasons for that to occur. And one is the sample size Bamba. This is a term that was coined by Schulz and Grimes in 2005. And they looked at the quality of a priori power analysis in randomized controlled trials. And the idea is that researchers conduct an a priori power analysis that will yield the sample size that they already had in mind. Okay, so basically they do a power analysis so that it returns the sample size that you wanted to recruit at the beginning of the trial. Then another one, it can be just invalid effect sided. So researchers deliberately choose a very large effect size that will return a very small sample size. And then another one could be inflated effect sizes due to flexibility in data analysis or publication bias. We will be talking about this in a little bit. So just to make the point here, so what or how a power analysis implicitly reveals the smallest effect size you care about. So here you can see the distribution of a coherence D of 0.2 when the total sample size is 30 participants. Okay, so that will be for an independent t-test, and the smallest effect size that you care about is determined by the statistical test, the alpha level, and the number of participants. So when you set the number of participants to 30 for an independent t-test, the smallest effect size that you would be able to observe that would reach statistical significance is an effect size of 0.75. So basically that means that you don't care about effect sizes that are smaller than 0.75 because those won't reach statistical significance. And this is a very odd thing to say, but this is what it reveals, because when you do a power analysis or you conduct a study with such a small sample size, you won't be able to detect effect sizes that will reach a statistical significance that are smaller than 0.75. And now, so why low statistical power? So now I'm going to be talking about the statistical power that we observed in these 350 studies. So out of these 350, we had to exclude a few, and we ended up with an analysis of 269 hypothesis testing studies that showed that the average statistical power was 11%. So the main implication is that with such a low power, the chance of detecting a true effect are extremely low. And just as a comparison, I mean, we are using hypothesis tests to decide whether a treatment is better or different to another treatment. And this is the chances of detecting whether such a difference exists is the statistical power, right? But when the power is so low, we don't have the sensitivity to detect that. And as a comparison, just flipping a coin, it's a 50% probability that it will land tails or heads. So if you are using hypothesis testing to make a claim or to make a decision about the superiority or not superiority of a trial, it might just be better to flip a coin. So why designing a study with higher statistical power is important? Well, there are two main reasons. One is the interpretation of null findings. So if a study is designed with very low power, for instance, 20%, a null significant result cannot be interpreted because it could be due to the fact that the effect size is smaller than expected or it doesn't exist. So if you conduct a study with very high power, let's say 90%, if you don't find a significant effect, you can be more certain that such effect doesn't exist. And then another important reason is that high statistical power narrows confidence interval. So for instance, here there are two examples. Imagine that we conducted a study with 20 participants and which yields a 95 confidence interval that stretches from minus 0.72 to 1.16. So the uncertainty around the effect size, the true effect size, is huge. And this is opposed to conducting a study with 200 participants, which might yield a 95 confidence interval that stretches from minus 0.75 to minus 0.23. So here the uncertainty around the effect size is much smaller, and this is preferable. Another reason why a study can contribute to research waste during the study design is the lack of transparency. So one example could be framing your study as confirmatory when it's exploratory. We discussed this in the paper with Di. And the point that we want to make is that exploratory research is valuable, but it should be transparently reported. And while in our experience, many exploratory research, even if it's exploratory, then it's reported and published as confirmatory. And this is not transparently reported. And that might increase the risk of type 1 errors, inflated effect sizes. So it's very important that when we're exploring and we are not testing a specific hypothesis, we are transparent on that. And then another one is vague and unfalsifiable hypothesis. Um, in our experience as well, researchers state vague hypotheses, and a vague hypothesis is easier to prove and is easier to obtain a significant result, because you can test it in multiple ways. And we discussed this in this preprint in 2000 that we published or we updated in 2025. And the point that we make is that the vaguer the hypothesis, the easier is to support it. And a vague hypothesis is not informative because you are not transparently communicating the effect size or the type of intervention effect that you want to show. Then we move to the next problem, which is selection bias. Selection bias comes into two flavors. One is publication bias, and another one is flexibility in data analysis, or also known as p-hacking. So here we can see this figure, and ODR stands for observed discovery rate, which basically is the proportion of significant findings reported in the literature. And for that, there were two studies published in the last years, and which found a proportion of significant findings of 73%, and another study of 81%. Okay, so in order to observe this percentage, okay, this is a function of the average statistical power of these studies and the proportion of true hypotheses tested. So, for instance, let's take the 73% observed discovery rate, okay, which is the black thick line. And we can see that to observe a 73% of significant findings in the literature, you either have to study hypotheses that all of them are true, and design studies that have a statistical power of 73%, okay? Or you can either study or test hypotheses with a lower proportion of truth, but with higher statistical power, okay? But even if we go here, let's take this example, okay? Studying hypothesis that all of them are true seems implausible, or I think it's an implausible assumption, okay? But then if we move to the other end, assuming that all studies conducted have very high statistical power, I think it's a very implausible assumption as well, because we know that the sample sizes are very small. So there are two factors here that can increase the number of studies reporting a significant effect, which will support the hypothesis stated. And this is publication bias and flexibility in data analysis. So here, for instance, if there is publication bias, studies reporting non-significant findings or no finding support for the hypothesis tested won't be published, will falsely increase the proportion of studies that show support. And then another factor that can contribute to falsely increase the number of studies supporting the tested hypothesis is flexibility in data analysis or p-hacking. Just as an example, in psychology, Sheil and her co-authors compared the proportion of studies reporting a significant finding in a standard reports, which is non-registered studies, and then in registered reports. And you can see that the proportion of studies supporting the hypothesis in standard reports was about 95%, whereas in registered reports, this proportion decreased to just about 45%. So this is a clear sign that there was a publication bias in this set of studies. And an example of p-hacking, for instance, can be testing an hypothesis by performing 5 independent t-tests, or testing 5 dependent variables just to test the same hypothesis. And here we can see the distribution of p-values under the null hypothesis, which is the blue color. So you can see that the distribution of p-values is uniform. So every p-value has the same probability of occurring. And then the orange distribution shows the effect of p-hacking. Okay, so if we set the correlation between these dependent variables at 5, and we conduct 5 independent t-tests to test the same hypothesis, we can see that the number of p-values falling below the significant threshold increases. Okay, and this is assuming that there is no true effect. That's assuming that the null hypothesis is true. So we can see that the p-hacking increases the number of significant p-values. And then we set out this study where we aim to assess the statistical power and whether there was a publication bias in the set of 350 studies that we sampled from 10 sports science journals. After removing a certain number of studies, we ended up with 269 independent p-values. Okay, again, these p-values are central to the hypothesis being tested. So all these tests, all these studies were testing an hypothesis. Okay, so we can see that the observed discovery rate was 68%. That means that 68% of these studies reported a significant p-value that will support the hypothesis tested. Then we can see the expected discovery rate. This is the average power of all the 269 studies. And the statistical power of these 269 studies, including significant and non-significant p-values, was 11%. And then the last term is the expected replicability rate. This is the statistical power of the studies that reported a significant finding or that supported the hypothesis. And for those, the statistical power was 49%. And this technique, which is called zeta curve analysis, you can determine whether there is publication bias when the upper bound of the confidence interval of the expected discovery rate excludes the observed discovery rate estimate. Okay, so we can see here that the upper bound of the confidence interval is 0.33. So it excludes the estimate of the observed discovery rate. And this allows us to claim that in this set of studies, there is publication bias. And this is reflected in the number of studies or p-values that are missing here. So the red line denotes a statistical significance. So all the studies that fall or that report a p-value which is transformed into zeta score. So the higher the zeta score, the smaller the p-value. So yeah, a zeta score of 2 point something is it's a p-value that it barely reaches statistical significance, but it's significant. And those falling on the left-hand side of the figure are non-significant. So you can see here that the distribution indicates that there are missing p-values that should be observed, but they are not. And then I'm gonna show you the consequences of selection bias and studies with underpowered designs. This is one set of studies that were replicated by the replication team or the replication project in sports science. So they attempted to replicate 25 studies, and here there are about 10 studies. So the blue dot line are those studies that were replicated. So it's the replicated effect size and confidence interval. And then the orange one is the original effect size and confidence interval, okay? And again, this is just a subset. So they conducted 25 replication, but here it's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so what you can see is that the replications were usually conducted with a larger sample size. Okay, larger sample sizes, we know that reduce the uncertainty around the effect size estimate. So you can expect that the confidence interval should be narrower, okay? And we can see that in many occasions, okay, the effect size is smaller than the original effect size, and that the confidence interval of the replication is also narrower as opposed to the wider confidence interval of the original study. And the main results of the sports science replication project was that 56% of the 25 analyzer replication studies had a statistically significant p-value similar to the original studies, okay? Then I think this is the most important take-home message. The median percentage decrease in magnitude from the original to the replication effort estimate equal to 75% for all the replication effect sizes. So there was regression. So basically what it means is that most of the replicated effects or effect sizes from the replication studies regressed or decreased. And then another result is that only 36% of replication and original effect size estimates were compatible. So basically, this means that they tested whether effect sizes or the effect size from the original study was compatible with the effect size from the original study. And they found that only 36% of these comparisons were compatible. Then here I'm showing you other example of meta-scientific studies that have also reported regression. So for instance, we can see the study of Syria et al. Published in 2023, where they investigated they were interested in the effect of physical exercise on cognition. So, sorry, all those are meta-analyses, okay? So the effect size in the original set of studies was a coherence D of 0.22, but then after adjusting for bias, the coherence D decreased to 0.05. And the common pattern here is that if you adjust for bias in pooled effect sizes in meta-analysis, most of them decrease, okay? We can see, yeah, for most of them or all of them, there is a regression. Then another type of research waste occurred at when reporting research data. So I'm quoting here Murphy, Caldwell, and Wen. This project faced, and this project refers to the sport science replication project. This project faced many practical challenges when preparing studies for replication, specifically the poor reporting of statistical information, the availability of original raw data. And another example is that out of the 350 hypothesis testing hypotheses, 57% could not be recomputed into an exact p-value due to poor reporting of statistical information or availability of original raw data. So for 46 out of the 81 studies that were excluded from the zeta curve analysis, 46 p-values could not be recomputed because there were missing information such as degrees of freedom, T statistics, or F-test ratios. Another good example is the study by Bohr, where they assessed the prevalence of a study sharing data and code in sports science journals from Q1. And we can see, for instance, that only 13 out of 299 studies shared data and none shared code. So what happens when the reporting practices are far or the reporting practices are poor, and when there is a lack of data sharing, so that it's not possible for peers to reproduce and confirm the findings. The lack of data sharing or poor reporting practices also hinders our ability to conduct meta-analysis, replications, secondary analysis, or new research projects. And then a benefit of full reporting and code sharing and data sharing is that it promotes trust and accountability in research. And here, finally, I will show you another type of research waste which can occur in meta-analysis. So we can see, or perhaps the best example is the case of the study conducted by Catholic, Sainini, and Nifius in 2023. So what they found is that in the 20 most, sorry, I think it's 20, not 30. In the 20 most cited meta-analyses in strength and conditioning research, almost 45 contained at least one effect size that was mistakenly calculated using a standard error rather than a standard deviation. And the problem with that is that the calculated effect size, it's much larger when you are used the standard error instead of the standard deviation. 45% failed to account for effect size dependency. And then we also conducted a study to assess the methodological quality of meta-analysis published in Sports Medicine. And those are just three instances or three findings that we found. 16% of the 96 meta-analysis contained that data. Only 16% of the 96 meta-analysis contained data to reproduce the study effect sizes. many meta-analyses combined the studies with different designs, for instance, combining within and between, and randomized controlled trials and non-randomized controlled trials. And the main problem with that is that basically you are doing a meta-analysis by combining or comparing orange and apples, because randomized controlled trials might control for bias, but then you are mixing this with non-randomized controlled trials, which might suffer from bias. Or just by combining within and between subject designs. And then, similarly to the catalog meta-analysis, we found that 34% of these 96 meta-analyses did not account for effect size dependency. And the problem of that is that meta-analysis assume, or random effect meta-analysis assume that effect sizes are independent. But when you are combining effect sizes from the same study, the assumption of independence is violated. And what happens is that the standard error of the meta-analytic effect size shrinks, and therefore you are more likely to reject the null hypothesis and observe a significant p-value, which might inflate the type 1 error of the meta-analysis test. And summary: research waste in the form of studies that do not answer the research question, inflated effect size, study designs with low power, poor reporting of statistical practice, and lack of data sharing, and low methodological quality of meta-analysis. All this contributes to research waste in the field of sports and exercise science. And my main point here as well is that we, and I include myself as a community, are not properly trained to conduct informative research. So just briefly, I'm going to be talking now about the drivers of research waste. It's just going to be very briefly, because I think we are running out of time. So the main one reason is that there are wrong incentives. So quantity over versus quality. So mass produce sport and exercise science research for career purposes. Reference for studies that report positive findings, and we compete for limited resources. Then another one is time constraints. So lack of time to develop expertise and skills, and also insufficient training at bachelor and master level. And then how we move from there then. So I think it's easy to say, but I really like this quote from Altman in that it was stated in the paper, The Scandal of Poor Medical Research. So I really like the quote: we need less research, better research, and research done for the right reasons. So how we can do that? So we can talk about long-term, mid-term, and short-term solutions. As mid-term solutions, we could reward researchers not for the number of publications, but for the quality of their studies. More time for improving research competencies, and improve statistical training at bachelor and master level. As I said, those are long-term solutions, and it will require changes in the system. As mid-term solutions, I suggest science as a collaborative effort where each member brings a specialized expertise. That could be achieved, for instance, in big team science. Okay, so in big team science, there could be a role for each member. So each member brings a specialized expertise. So there could be experts in developing a research question. Then there could be methodologists, applied statisticians, then experts in data collection, analysis execution, experts in reporting guidelines, interpretation of effect sizes, and then how the data and the material that should be made available to the research community will be treated. So the main point here is that the goal is not to conduct experiments alone or with a small group of collaborators, which may lack expertise in some areas. I mean, as I said, there is a lack of time to gain new skills and to gain expertise. And we cannot expect that a single researcher can know everything about every single stage of the research process. So the goal is to support and enhance collective scientific research. And this is what I just described. But ideally, perhaps I'm too naive, but there could be theories to develop frameworks or hypotheses to explain phenomena, methodologies, data collectors, experts in interpreting effect sizes, and data stewards to manage, curate, and maintain data sets to ensure fair principles and reproducibility. And just to end the presentation, just remember that the 12th point in the Declaration of Helsinki states that medical research involving human participants must be conducted only by individuals with the appropriate ethics and scientific education, training, and qualifications. And the last point is about the short-term solutions. I think a very easy one, and which has already been mentioned in the literature, in the study by Saineni, is collaboration with applied statisticians. So we should promote collaboration with methodologists and applied statisticians from the beginning. So they should be involved in the design of the study, the conduction of the a priori power analysis, the data analysis, and the reporting of results. And then perhaps a last solution is the use of registered reports. However, one caveat here is that you may argue that if the research community is not properly well trained, then the reviewers that will review the stage 1 of a registered report might not have the skills either to improve the authors, to help improve the authors, the quality of the paper, of the study that they want to conduct. So that might be that's the reason why there is this question mark. And yeah, that's all for now. And thank you so much for having me and the opportunity to deliver this presentation.
Thank you, Cristian.